Good evening. I'm Professor Sally Shortall, co-chair of the Public Lectures Committee. Welcome to tonight's Insights virtual lecture. It's titled Everything from Nothing, How Our Universe Was Made by Professor Carlos Frenk. I will be back after the lecture in about 45 minutes for a live Q&A with the speaker. If you would like to ask a question, you can either do it on the YouTube live chat box that's on your screen or via Twitter at InsightsNCL. Here to introduce tonight's speaker is our Pro Vice Chancellor for the Faculty of Science, Agriculture and Engineering, Professor Phillip Wright.
Thank you very much for attending our Insights virtual lecture series. My name is Professor Phillip Wright and I'm the Pro Vice Chancellor of the Faculty of Science, Agriculture and Engineering at Newcastle University. And I'd like to welcome and thank our guest speaker today, Professor Carlos Frenk from Durham University, who's going to speak to us on the topic of everything from nothing, how our universe was made. Carlos Frenk earned a degree in physics at the National Autonomous University of Mexico in 1976. He then went to Cambridge, where he read Part 3 of the Mathematical Tripos in 1977 and received a Ph.D. in astrophysics in 1981. In the 1980s, Frenk was part of a collaboration with Marc Davis, George Efstathiou and Simon White that established the validity of the cold dark matter theory for the formation of galaxies and other cosmic structures, now the accepted interpretation in cosmology. In 2001, Frenk became the founding director of Durham University's Institute for Computational Cosmology, where he's continued to specialise in large supercomputer simulations of the formation history of the universe. He was elected a Fellow of the Royal Society in 2004. In recent years, Frenk has been using computer simulations to explore the cold dark matter model in the previously inaccessible regime of the Milky Way and its satellite galaxies. I really hope you enjoy the talk today. Thank you all very much.
Good evening. I'm sorry I cannot be there with you in person, but I hope you will still enjoy this virtual lecture. The title of the lecture is Everything from Nothing, or How Our Universe Was Made. As you can see, this lecture has to do with cosmology, which is the science of the universe, which is actually one of the oldest sciences ever. And it has some of the most fundamental questions that human beings can ask. Questions such as how did the universe begin? What is it made of? How did it evolve to its present state? What does the future hold? Now, these are questions which have been asked by humanity, by ancestors, really pretty much since the beginnings of civilization. And one could even argue that civilization began when our ancestors started asking these sort of questions. Now, of course, it's not just physicists like myself, cosmologists, who are trying to answer these questions. There are other people in other disciplines who also try to have a go at answering some of these questions. But what's special or unique about physics and modern cosmology is that we have a very well-defined, rigorous methodology to try to tackle these big questions. And that is based on the laws of physics. Laws of physics, as I'm sure you all know, are the general rules about natural phenomena. They are usually derived, in most cases, empirically and expressed mathematically. For example, Newton's law of gravitation, Boyle's law of gases, quantum mechanics, relativity. And what all these laws of physics have in common is that they're experimentally verified on Earth. And one of the great mysteries of modern science is the fact that these laws of physics that generally we discover on Earth, we test them, we verify them with experiment here on Earth, they seem to apply not just on Earth, but everywhere in the universe, in all places and at all times. In other words, these laws of physics, for some profound reason, seem to be quite universal. Now, the building blocks of the universe are galaxies. It's an example of a galaxy similar to our own Milky Way. Galaxies are collections of anywhere between a few million to 100 billion stars. Our Milky Way galaxy is similar to this one, and we live about in Durham, 2/3 of the way from the center of the Milky Way. And here's a picture of the institute in which I work, is the Ogden Center for Fundamental Physics. and that some of my colleagues feel it's actually at the center of the galaxy. I keep having to tell them that that is not the case. We're 2/3 of the way from the center of the Milky Way. Now, to get you into the right astronomical cosmic mood, let me show you a animation, a movie made by a colleague of mine in Hawaii, Brent Tully. And this movie is a tour of the local universe. And what you're going to see here is stars, galaxies that are out there. This is based on data from the real universe. And here we are. We start our journey traveling towards the constellation of Orion, which you can see there. Next to it is the Orion Nebula, which is a cloud of gas and dust where new stars are continuously forming. The Milky Way is forming a new star at the rate of about new stars rate about 1 every 100 years. Here's another nebula similar to that one. That's a famous one, has a name, it's called the Horsehead Nebula. But in fact, not all of these clouds of gas and dust are birthplaces of stars. Well, some are. Actually, this is another one. This is the Carina Nebula. And you can see here that stars tend to form not just singly, but often in groups of a few. So as I was saying, not all nebulae are actually birthplaces of stars. Some of them are exactly the opposite. This is, in fact, a burial place for a star that once was like the sun, ran out of nuclear fuel, exploded, blowing out its outer layers and leaving behind something called a pulsar, which you might see pulsating pulses of light from the center. Now, this is the only bit of artistic impression in this movie. We're going to leave the galaxy. Of course, we cannot leave our own galaxy and look at it from outside. So, but this galaxy is very similar to the Milky Way. The size of a galaxy is about 30,000 light years across. And you can see our galaxy surrounded by this retinue of neighbors. It's 30,000 light years across, meaning that it'll take 30,000 years for a signal from one side of the galaxy to reach the other end. Now, here is a very famous galaxy called the Andromeda Galaxy that is our nearest big neighbor. The Andromeda Galaxy has a companion called M32, which itself has its own clouds of gas and dust, and it's making stars. So the Andromeda Galaxy is about 2 million light years away. So it takes a long time for light to travel even from our nearest neighbor to ourselves. We're going to head eventually to this lump of galaxies here called the galaxy cluster, but before the Virgo cluster, in fact, before we do that, we'll take a little detour to admire these incredible things that nature has made. These beautiful galaxies with spiral arms, sometimes interacting with companions. And you can see here that the distribution of galaxies in the universe is not random. There are clumps of galaxies, there are so-called filaments of galaxies, and all these, as we shall see, reflects physical processes that happen at the Big Bang, at the very beginning of our universe. So we're heading towards the Virgo cluster of galaxies, which is about 10 million light years away, 30 million light years or so. In the center is a collection of about a few thousand bright galaxies, and in the center of the Virgo cluster, there's this famous galaxy called M87. It's famous for many reasons. One is you see a little jet of material coming out there because in the center of this giant galaxy, there is a gigantic black hole that, and you saw that little jet is a little bit of the leftovers from the fact that the very big black hole in the center, and it has about 100 million times the mass of the sun, is eating all the stars around it. And some of you may have heard actually that the Nobel Prize in Physics awarded last week was awarded to 3 people, 2 of whom, Reinhard Genzel and Andrea Goetz, discovered or mapped or detected, I should say, very directly the gigantic black hole at the center of our own Milky Way galaxy. And they were given the Nobel Prize for that, together with the great mathematician Roger Penrose, who predicted that black holes should exist. But let's get back to our story. And the first question I want to tackle is, what is the universe made of? And innocent sounding question. In fact, behind it lies one of the most stunning discoveries of science of the last few decades, because it turns out that our universe, the contents of our universe are actually quite bizarre. And let me show you that with a pie chart. Here are the contents of the universe, and the ordinary matter of which we are familiar makes up only 5% of what the universe contains. This is normal matter made of ordinary atoms, the atoms of the periodic table, the ones we're familiar with, carbon, oxygen, nitrogen, and so on. They make up only 5% of what the universe contains. 25% is also matter, but it's a different kind of matter. It's called dark matter. This dark matter is not made of atoms. It's made of something more exotic. And as the name indicates, it has the property that it does not emit light at any wavelength. So that's 25%, 5% ordinary matter, but the lion's share of the universe, 70% of the contents of the universe, is something that we call dark energy. Now, we know, of course, a lot about ordinary matter, but we still know quite little about dark energy and dark matter. So let me tell you particularly about dark energy. We know very little about dark energy. Let me tell you briefly what the dark energy is, and at the end of a couple of slides, you'll be more or less at the same level of expertise as the professionals who make a living from studying these sort of phenomena. Now, we've known for a long time, in fact, since the late 1920s, we've known that the universe is expanding. That was discovered by the American astronomer Edwin Hubble in the days when people were allowed to smoke in their offices. And Hubble made a graph, a very famous graph called the Hubble diagram, in which he plotted the velocity at which galaxies are moving as a function of how far away they are. And what he discovered is that the farther away the galaxies are, the faster they're moving away from us. And in fact, all galaxies, with the exception of Andromeda that we saw before, and all galaxies are moving away from us at a distance, at a velocity that increases in proportion to the distance. What Hubble had discovered was that the universe is expanding. All galaxies are moving away, not just from us, from every other galaxy. So that we've known for almost 100 years, but at the end of last century, a very dramatic discovery was made by scientists in various countries around the world who were studying very distant supernovae. These are stars that explode, they're very bright. You can see them at very large distances, and then you can try and piece together the way in which the universe is expanding. And the big surprise was that these data showed that not only is the universe expanding, but the expansion is accelerating, meaning the universe is expanding faster and faster and faster and faster. And that came as a big surprise, because physicists thought that the opposite should be true. The expansion of the universe should be slowing down because the matter in it pulls back because of gravity, and that should be slowing down the expansion. What was discovered was exactly the opposite, that the universal expansion is accelerating. And what that tells us indirectly is that the universe must be full of something that's pushing, acting against gravity to make the expansion faster and faster and faster. We don't know what it is, and in science often when we don't know what something is, we give it a fancy name and we call this dark energy. And even though we don't know what the dark energy is, it's sufficiently interesting and exciting and well established, the evidence for it, that the discovery of dark matter earned the Nobel Prize in Physics to 3 colleagues in 2011. Now, so what is the cosmic dark energy? As I said, we don't know much about it. It's some form of energy that's everywhere in the universe that produces a repulsive force. It opposes gravity, causing the universal expansion to accelerate. And we don't know what it is, but because most of the universe is empty, it must have something to do with empty space, with the vacuum. And that's about as much as we know about dark energy. So I promise you would be up to the same level as experts. There you are. That's what pretty much what experts know. Well, many people trying to study and measure the dark energy. It's about a good summary of the state of knowledge in the subject. So let me go back to more familiar territory, dark matter, where we know a lot more about dark matter than we know about dark energy. We know that it makes, as I said before, 25% of what the universe contains, and we know that it's dark, it doesn't emit light. Now, so the existence of dark matter was inferred originally by looking at the way in which stars move round and round galaxies. So stars are going round and round, and the reason they don't fly apart is because the force of gravity of something, it's keeping them in place. And this gravitational physics was discovered 350 years ago by Isaac Newton, whom you see here. And with Newton's law, we can figure out how much matter a galaxy has to have in order to keep the stars in place. And when you do the calculation using Newtonian gravity, you find that the material you can see in the form of stars and gas clouds in the galaxy is grossly insufficient to explain the speed at which the stars are going round and round the galaxy. If all the galaxy had was the matter that we can see, the stars would have already flown apart. So the inference is that there must be something we cannot see, dark matter, that is keeping the galaxy in place and allowing the stars to keep going round and round the center of the galaxy. Now, the other day, before lockdown and all these kind of things, I was actually in London, walking in the streets, thinking about some slightly complicated aspect of gravity, of Newtonian gravity. I was very fortunate that I ran into Newton, or at least into the modern incarnation of Newton. So here you see Newton, who's come back to life as a musician, and you see it is Newton. Yeah, the hair is not only the hair is the same, the nose is the same, the mouth is the same, and so this is Brian May, of course, musician, famous musician. He's also an astronomer, and that's how I know him, not as a musician, but as an astronomer. He has a Ph.D. in astronomy, and but he decided to have a different career from the one he had trained to do. So Brian, or Isaac, explained to me fine points about Newtonian gravity. So the way you should think of a galaxy is just a little pool of light, stars and gas, embedded in a big lump of something that just doesn't shine, a lump of dark matter, which physicists call a halo of dark matter. Now, and it is what keeps galaxies in place. So what is the dark matter? Well, the current view, accepted by most cosmologists, is that dark matter is some form, it's clearly not atoms, and it's maybe possibly, or very likely, some form of elementary particle that was formed in the early universe, and it is different from particles in ordinary atoms. Here's a cartoon of the Big Bang. 13.7 billion years ago, the universe began with a big explosion, and you see various events here. I'll come back to this diagram later, but when the universe was very young, about 10 to the minus 10 seconds old, that's when we think the conditions were ripe for these elementary particles to form, to emerge from the Big Bang, and these are the particles that we think are the dark matter. I'll tell you more about that in a minute. That elementary particles, the best candidates go by the collective name of cold dark matter. Now, in fact, if these ideas are correct, the world is full of dark matter. The Earth has lots and lots of billions, in fact, of particles of dark matter crossing our bodies every second, but they don't interact. That's why these particles are dark, because they don't interact with anything. So they go through our body, and they don't cause any damage, just go straight through, and but none the wiser. But there are experiments trying to detect these particles that are coming onto the Earth from outer space. These experiments usually take place in mines in order to filter out all sorts of other debris that rains into the Earth. And in fact, here, not so far from Newcastle, there is a mine in Yorkshire, North Yorkshire, called the Bowlby Mine. It's a salt mine. And there in the mine, there's an experiment trying to detect these dark matter particles from the halo of the Milky Way. Of course, they haven't found it yet, otherwise we would know about it. Now, so why is this dark matter so interesting? Well, for two reasons. One, of course, is we want to know what the universe is made of, and this is most of the mass in the universe, most of the matter is this dark stuff. So that's one reason. But there's another reason, which and why there's so many people in the world, including at my institute in Durham, dedicating their lives to try to understand dark matter. And that the reason is simply that without dark matter, we would not be here. dark matter is responsible for all the structure we see in the universe. So let me now come back to the third of these questions. How did the universe evolve to its present state? Well, let me go back. I will go back to my cartoon in a minute. Let me just reiterate what you said, that it is the gravity of dark matter that is responsible for the formation of galaxies and all cosmic structure. So let me tell you how that works. So here's my cartoon of the Big Bang. And the story, this cosmic genesis story, begins very early on, very soon after the Big Bang, when the universe was very, very young. In fact, 10 to the minus 35 seconds old. That's a decimal point, 34 zeros, and a 1. That tiny fraction of a second after the Big Bang, that is when the story begins. And that is very, very early, very soon after the Big Bang. And it is the early time at which cosmologists and physicists can talk about physics and still keep a straight face. Before this, we don't really know what happened. The laws of physics break down. So we don't really know what was there before the Big Bang. We know there was a Big Bang. We don't know what went bang, but what we do know are the processes that began to unfold at this tiny fraction of a second after the beginning. And this brings me back to the title of the lecture, Everything from Nothing, How a Universe Was Made. So what do I mean by this? What do I mean by nothing? Well, we all may have our ideas of nothing, but in physics, there is a very precise definition of nothing. In fact, nothing is called the vacuum, and the vacuum is a state in which everything's been, imagine a cavity. Imagine you take everything out of this cavity. You have a very, very powerful pump and you extract even the last atom. That would be a vacuum. But then you go to this cavity, and which has been denuded, it's been, all its contents have been taken out. You look at it carefully enough and you will find a surprise. You will find that even though you thought it was empty, it is not completely empty. It would look like this. These are balls represent matter and antimatter. And we know that when matter and antimatter come together, collide, they annihilate, producing energy. Now this energy is a vacuum energy, and out of the vacuum energy comes this matter and antimatter that annihilates back into energy, which then decays into matter and antimatter, and the cycle is going on and on and on. This is the vacuum energy, and in fact the vacuum, far from being completely empty, is bubbling with this matter and antimatter that appears and disappears very, very quickly. That is the essence of a branch of physics called quantum mechanics. So I know this is a bit complicated, but the message is that the vacuum is full of energy. It's called the vacuum energy, and this is going to play a key role in understanding our universe. Now, so as I said, the story begins very soon after the Big Bang. When the universe came into existence, it had an excess of this vacuum energy, and it tried to shake it off by expanding very quickly during a very brief period of time, as represented here by this sort of line here. The universe expanded exponentially, a little bit like the coronavirus, propagates exponentially, meaning it doubles, the infections double in time, double every fixed week or few days or whatever. The universe expanded exponentially for a very brief period of time, and it grew from a tiny, tiny spot to the size of a football in about 10 to the minus 35 seconds. This period has a name. It's called cosmic inflation. Now, as a result of cosmic inflation, the universe shook off this excess of vacuum energy. But in so doing, it created small ripples in the energy density of the universe. So the universe was very smooth, but as this vacuum energy decayed, it acquired small deviations from uniformity, small spots, if you like, regions where the energy was ever so slightly bigger, or the mass, or the density, or the temperature than in other regions. And these are called quantum fluctuations because this is to do with quantum physics. And so these small perturbations or small irregularities, let's call them that the universe acquires coming out of the inflation period are known as quantum fluctuations. So these are tiny, 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 tiny fluctuations in the energy density of the universe from one place to the next. Now, the amazing proposition of cosmology is that everything we see in the universe comes from these quantum fluctuations. And that is one of the most profound propositions that any scientist can make. That a galaxy with its 100 billion stars originated from a tiny little ripple produced by quantum processes that happen during or very soon after the Big Bang. I'm going to show you some evidence for this in a minute, but these small ripples, which are really, really tiny, are amplified by the force of gravity produced by the dark matter. And so these are the gravity of dark matter takes hold of these small irregularities and causes them to be amplified. And let me, I'm going to show you a movie of that in a second, but before that, let me reiterate that in physics, it's all about providing evidence. It's all about testing hypotheses. So in physics, you're allowed to make a wild proposition. So long as your wild proposition is testable, then you're doing physics. You get paid at the end of the month. What you're not allowed to do is to make hypotheses that are not testable. Well, you are allowed to do it, but then people don't look up to you very well. So I'm actually going to show you a movie of how this gravity amplifies these fluctuations. But before that, I want to jump directly to the evidence that this very exotic phenomena that I'm talking about almost certainly happened in a universe. So we know that the early universe was very hot, it was very dense, it was very hot. And as the universe expanded, then it cooled down. And but the very early universe, or the early universe was foggy because it was still so hot. It was cooling down, but it was so hot that atoms didn't really exist. They were broken up into atomic nuclei and electrons. And the heat or the light from the Big Bang continually scattered off these electrons, causing the early universe to be foggy. However, and this is one of the landmarks in the history of the universe, about 350 years after the Big Bang is just the wink of an eye. Remember, the universe is 13.7 billion years old. This is the equivalent of the human equivalent of 1 day old. At that very young age, the first atoms formed, and the electrons that were causing this fog in the early universe became incorporated into atoms. And so the radiation of the Big Bang was freed up and was able to escape and propagate throughout the universe. So this is the first light of the universe. It was emitted 350,000 years after the Big Bang. And as I will show you in a minute, we can see that light, and that brings us news about the physics of the early universe. Now, so as I said, as the universe expands, these radiation, the heat, if you like, of the Big Bang, which is in the form of light, cools down. And in fact, the universe is old enough that by today, the radiation of the Big Bang has cooled to a mere 2.7 degrees above absolute zero. So it's very cold, but it's not zero. Now, that radiation was in fact discovered in 1964 by these two chaps, Arno Penzias and Bob Wilson, who accidentally stumbled across this incredible discovery. They didn't even know about cosmology, didn't know about the Big Bang. They had built a radio telescope that you can see there, and they were trying to detect radio waves from the sun. And they were very annoyed that wherever they pointed the telescope, there was this signal that came from everywhere in the sky. It was very weak, but it was definitely there. Accidentally, and unbeknown to them, they had detected nothing less than the heat left over from the Big Bang. And because this heat is now so cold, then it's in the form of microwaves, and this is called the cosmic microwave background radiation, and it's everywhere. It's in this room, it's everywhere. There's about 100 particles of light per cubic centimeter in this room, in any room, that come directly from the Big Bang phase of the universe. Let's go back to our story about the everything from nothing. So we've seen the emergence of these quantum fluctuations during the epoch of inflation, and I've already forewarned you that these quantum fluctuations will be amplified by the gravity produced by dark matter. I'm about to show you a movie to illustrate how this works. But when the microwave background radiation is emitted 350,000 years into the life of the universe, these fluctuations have grown and produced a pattern of hot and cold spots in the radiation that physicists understand, and the properties of which were predicted in great detail in the 1980s. So the sky, if we make a map of the temperature of this radiation coming from the Big Bang, the temperature should not be the same everywhere. There should be a pattern of hot, cold spots, as you can see there. Well, these hot and cold spots were discovered in 1992 by a satellite called the COBE satellite. And here is a very famous map. It's a map of the temperature of the sky. And as you can see, it's not just one color, meaning that there are points that are hot and other points in here that are cold. Now, this initial discovery earned the made headline news across the world. Here is the front cover of the independent newspapers in the days when science other than coronavirus made it to the front cover of newspapers. It's in the 24th of April, 1992, under the headline of How the Universe Began. Now, I hope you forgive me. I'm going to leave modesty aside. So I played a role in this discovery, and you can see here, it says clearly somewhere here, it says, oh yeah, Carlos Frenk, an astronomer at Durham University, said yesterday, oh wow, you can have no idea how exciting this is. That was my great contribution to the discovery of the microwave background and my great contribution to science. And one thing is that my wife is under instructions that my epitaph on my grave should say, oh wow, that was really a wow moment, because it brought everything we knew about the universe together, and it provided empirical evidence that these ideas that seem very crazy, quantum fluctuations, expansion, exponential expansion, have cold dark matter, have some truth to it. And I will give you even more compelling evidence in a second. Before that, this radiation was, this discovery earned George Moore in Berkeley, California, good friend of mine, the Nobel Prize in 2006. The radiation was remeasured 10 years later with greater resolution by another satellite from NASA called WMAP. And then the definitive map we have is from a European satellite with British participation called Planck, the Planck satellite. And you see here this amazing pattern of hot and cold spots. Now, I said before that physicists understand this pattern in great detail. I don't want to go into technical details here. Just suffice it to say that this plot describes this pattern in mathematical terms of hot and cold spots. For those who know a bit of physics, this just tells us the relative or the temperature difference between 2 points on the sky in this radiation as a function of how far apart these points are. But the details don't matter. The point I want to make is that the mathematical description of this pattern is complicated. It has structure that you see here, and it was predicted by Jim Peebles in 1982. So this was the theoretical predictions from 1982 by Jim Peebles, who won the Nobel Prize in Physics last year. And Jim is the mentor of my generation of cosmologists. I know him very well. And I was so pleased when he finally got the Nobel Prize. He should have got it before, and for other reasons. And he's not just one of the greatest scientists that I've come across, but also a great person. He is kind, he is humorous, he has time for everybody and for everything. So a real example, both of the part of science and of what's best in humans. Now, here is a comparison between the predictions by Jim Peebles in the 1980s, shown in green, and the measurements of these radiation, or these temperature differences in the radiation, shown here in red. And as you can see, the agreement is perfect. Now, so I need to pause here for a second, because I just want to impress on you how momentous this plot is, and that this is one of the landmarks in physics, one of the high points, certainly of my life as a scientist, and I think of that of many other scientists, because somehow, for some reason that we don't understand at all, in this little planet, 2/3 of the way from the center of a galaxy, a species of living organism has evolved that is capable, on the one hand, of inventing the language of mathematics and discovering the laws of physics and making predictions for the properties of the universe right back when it began. That is the green line. And this same species of living organism can also build machines that get launched outside their planet and can make these exquisite measurements that you see here. These are tiny, tiny different fluctuations, 1 part in 100,000, the difference between the hot and the cold spot, and that is measured with exquisite accuracy. So I think this is a tribute to humanity, and brings out clearly what is best about humans. Now, so I'm nearly at the end of this story. How do we go from this pattern of hot and cold spots in the heat left over from the Big Bang to galaxies? Well, that turns out to be, if not straightforward, at least a very tractable problem using big computers. So the idea is to take these small fluctuations, this pattern of hot and cold spots, and then see how they would evolve according to the laws of physics. That's called a computer simulation. And we know what the starting conditions are. That's that pattern of hot and cold spot, those quantum fluctuations from inflation. And what remains to be done then, we know the equations of physics, is to solve the relevant equations of physics. I've listed some of them here in the expanding universe, starting from that initial state. So we program large computers. This is one of the biggest supercomputers in the country. It's in the University of Durham, and all it does is compute simulated universes. So we program the computer with efficient ways to solve these equations of physics. We then go away on holiday, come back and see what has come out of the computer, and then we try to compare that to the real universe. Now, let me show you a movie made from one of our computer simulations. I've been trailing this movie now for quite a while, but this movie that shows how these small quantum fluctuations from the early universe are amplified by the force of gravity into the structures that we see in the universe around us. So here we are very soon after the Big Bang. This is in billions of years. This is 0.05 billion years, 50 million years after the Big Bang. And these small irregularities are these patches of over dense and under dense regions that came out of these quantum fluctuations of inflation. And as the universe evolves, the force of gravity amplifies some of these fluctuations, because in a region where the density was slightly higher than average, because there's more mass there, there's also more gravity, and that mass then attracts, usually flows along these filaments. You see here these lumps all coming together because this object in the middle is massive and is attracting all these other lumps from the surrounding, and that process continues. It's called hierarchical clustering. The small objects just get bigger and bigger and bigger with time. So what we're looking at here is just dark matter, and I will show you in a minute how the visible matter also responds to this force of gravity and eventually produces the visible galaxies that we see today. Before I show you that, let's just take a tour of the universe. Now it's just the universe today. This is what we would see if we were able to put on dark matter glasses and fly through the universe at a huge speed. That's what we would see. Lots of lumps of dark matter arranged in this cosmic web, a filigrane of filaments that surround regions of lower density. At the intersection of these filaments, these big lumps of dark matter form. These would be the clusters of galaxies, like the Virgo cluster that we saw earlier on. So all this richness of structure, this huge variety of structures that we see here, they all emerge from these small fluctuations in the early universe. And now let me show you now what the ordinary matter does. Of course, the ordinary matter feels the gravity of the dark matter, and not surprisingly, it would also accumulate into these lumps of dark matter. It is still dark matter, but in a minute, we're going to cut to see the evolution of gas. This is from a simulation called the Eagle simulation, carried out that big supercomputer in Durham. Now, this is not dark matter, this is gas, ordinary matter, hydrogen and helium gas that come out of the Big Bang. And you can see it's falling into this dark matter halos, but it's spinning. And as it spins, you see how a larger and larger object begins to form, which is rotating, it's very thin. Here we cut to stars. This, as I say, is just solving the equations of physics. That's all that we put into these simulations. And we go back now to gas, and you see kind of objects that emerge. They look a lot like the real galaxies. And I'll show you some images in a minute. This took many years of very hard work by a big team of people, not just in Durham, but across the world, to get to the stage where we can solve the right equations in order to make objects that look like this. So here are some images of galaxies. These are not galaxies from an atlas of the real universe. These are virtual galaxies, galaxies that we made in a computer from the simulations which just solve the equations of physics. So let me almost conclude. Just to summarize what I said so far, we have these small perturbations, quantum fluctuations from the universe. We feed those into a computer, and then the objects that come out, simply through the laws of physics, are very similar to the galaxies that we see today. And this is the evidence that all these crazy ideas I talked about at the beginning of this lecture have some truth to them. So let me summarize. I told you a story that begins very soon after the Big Bang, where the universe inflates exponentially, and as a result of this vacuum energy, it acquires small inhomogeneities that we can examine in the heat left over from the Big Bang. And these small fluctuations are the source of all the galaxies and all the structure we see in the universe today, as we can compute by using computer simulations. So let me finish off with one of my favorite paintings. This is a triptych by the 15th century German painter Dürer. It's a triptych. It's called The Garden of Early Delights. It has 3 parts. In here, in the middle, is Earth. And in Earth, I put in the question, what is the dark matter? And that question I associate with some early endeavor, because I think we're on the verge of actually discovering the particles that make dark matter. The evidence for it is compelling, and it's now incumbent upon experimental particle physicists to detect these dark matter particles that are everywhere around us. So that's an earthly endeavor. Here on the right side of this triptych is the question of what is the dark energy? And I put that in hell, which is the right part of the triptych, because that really is a hellish question. And I have no idea what the answer to this is. I don't think my generation of physicists will find out the answer. It is the next generation, maybe hope some of the people, young people in the audience, who might eventually answer this question. And then the left side of the triptych of the Garden of Early Delights is heaven. And the question I've assigned to heaven is possibly the most profound of all questions. How did our universe begin? And we don't know the answer to this. As I said before, we know there was a Big Bang. We don't know what went bang. And the reason we can not even begin to tackle this question is because we do not have laws of physics that apply right at the moment of the Big Bang. So this is for future generations to ponder about. But humanity has decided to spend a lot of money, billions of dollars or pounds or euros, in trying to answer this question by deploying telescopes of various sizes, various capabilities, both on the ground and in space. And of course, what underpins all this technology, including computing, is the great powers of the human mind, which have brought us to where we are today. So there's been enormous progress in understanding our universe over the past 30 years. But I think the best is still to come. Thank you.
So I would like to thank our speaker, Professor Carlos Frenk, for a really super interesting talk. Carlos, I really enjoyed it. I loved your use of images. It was really, really interesting. So we have a number of questions from the audience, which I will put to you. So Nick asks, the Big Bang resulted in sufficient matter for multiple billions of galaxies, plus the associated proportions of dark matter and dark energy. But do our theories about the Big Bang mandate our assumption of such a large amount of product? Or are the models equally consistent with the universe weighing 1 kilogram or 1 gram? Is the answer, it just did?
Well, this is a very interesting question. We know how much the universe contains because we can, for example, count how many galaxies there are. We can count how many stars they have. And we can, if you like, weigh the galaxies or weigh the stars using various laws of physics. So we know it's not a kilogram. We know it's a lot more than that. But, and we know to quite high precision, actually, to a precision of less than 1% error, we know how much the universe contains in its various forms. Now, but where does that come from? Where was all this energy, all this mass made? And that's a very interesting question. Now, the current view, in fact, is that everything we see in the universe, all the matter, all the energy, it's in fact the residual from this vacuum energy that I was talking about during the lecture. So if you remember, I talked about the universe being born with an excess of vacuum energy, and that vacuum energy was shaken off during the epoch of inflation. Well, it's that excess of energy, which we see today in the form of everything, matter, stars, and so on. The person, or one of the first physicists who thought or talked about inflation, who predicted that inflation should have happened, Alan Guth from the Massachusetts Institute of Technology, calls this the ultimate free lunch. So everything we have in the universe is a free lunch. It is this vacuum energy that was there for some reason that we do not understand from the beginning. So in a way, we are part of this free lunch. That's where we think mass and energy came from.
Great, thank you. There's another question here. If the universe is expanding at a faster rate, where will it all end?
Oh, this is a very, very interesting question that worries many of us. Now, so the most likely, or we don't know for sure, but the most likely outcome or the most likely state of our universe is that it's actually infinite in extent, and that the future will extend to infinity. So until, well, when I was a student not that long ago, the preferred view of the universe, but there was no evidence for this, was that we lived in a cyclical universe that would expand from the Big Bang, reach a maximum size, and then gravity will bring it all together, causing it to recollapse, perhaps in a cyclical way with various cycles of Big Bang, expansion, and Big Crunch. That's where Big Crunch comes from. But I think we now know better because of this dark energy. And it looks like, unless the dark energy does something very bizarre in the future, which it might do since we don't know what it is, but if it keeps behaving as it is behaving today, the universe will continue to expand forever. And it will become bigger and bigger, and it become cooler and cooler and cooler and duller and duller and duller, because all the stars will eventually die, since stars are fueled by nuclear power, and they will eventually run out of the nuclear fuel. And so stars will die out, galaxies will die out, and then even worse, matter will begin to disintegrate, because the particles of which atoms, the atoms that I'm talking about, the ordinary atoms that we are made of, they are finite, they eventually decay. And so the future is very gloomy indeed. We will end up in what I like to call a vast frozen expanse. It won't be frozen, but it'll be very cold, it'll be very dark, and it'll be extremely boring. It will just be a sea of particles and very, 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 very dim radiation, and that really not a good place to be. However, there's no reason to be alarmed, because this future won't happen for a very, very long time indeed, not measured in billions of years, but in power 10 to many, many billions of years. So it's a very long-term forecast for the future of our universe. But that's where it seems we are heading, to that unexplained, if you like, state where everything has decayed, where nothing really remains.
Great, thank you, Carlos. There's one here from Dave. Do you believe the noise found all around us is actually from the or a Big Bang, or could it be that we are and have been moving through the aftermath of a supernova?
Sorry, I didn't catch the first. You said, do you believe that?
The noise.
The noise.
Yes.
Well, so certainly everything in a universe, it emanates from the Big Bang. So that's where, in fact, even by definition of universe, the universe is everything. So, and we're part of that everything. And the Big Bang is, in fact, where that everything actually came to be. Now, I don't think we are part of a supernova explosion directly, but, and this is very fascinating, we are in a way, or we incorporate in ourselves bits of supernova. So let me elaborate upon this. You could ask a question, well, where do the atoms, the ordinary matter I'm talking about, the 5%, where do they come from? So where does the carbon and the oxygen and the iron and the gold, where do these elements come from? Well, it turns out, and this is something that, in fact, Jim Peebles actually first worked out, the Big Bang made only very simple chemical elements. It only made hydrogen and helium and very, very small amounts of lithium and beryllium, which are very simple atoms. The rest of the atoms, the interesting atoms, the atoms that we are mostly made of, at least oxygen, carbon, and so on, they were made in the centers of stars. As I said before, stars are nuclear reactors. They have fuel, and they turn hydrogen and helium into more interesting, more complicated atoms, such as the atoms we're talking about, carbon, oxygen, and so on and so forth. So these heavy elements, as we call them in astronomy, these more complicated atoms, they are manufactured in the centers of stars. But big stars explode, supernovae, as we just, as the person who has the question knows about, and the supernovae spread out these atoms into the cosmos, And these atoms were then incorporated into subsequent generations of stars and indeed into planets, and eventually made their way to us. So the atoms of which we are made, apart from some of the hydrogen, which goes back to the Big Bang, but all the other atoms were actually manufactured inside a star, a big star that blew up and spread these atoms around until they became incorporated into planets and people. So we could say, if you're ever feeling depressed, you shouldn't be depressed, because we are actually made of cosmic atoms. We are the result of a great explosion. We are made of cosmic matter. Now, people who are very depressed say, no, that is not true. We're nothing other than nuclear debris. So it depends on your outlook on life. I'm an optimist, so I always rejoice thinking that my atoms came from an explosion, a supernova explosion that manufactured the atoms of which I am made. I don't regard myself as just nuclear debris.
Thank you. There's a question here from Bert. Is it possible that dark energy existed before the Big Bang?
That's all these fascinating question as well. I don't know the answer to this one, because I don't know what happened before the Big Bang. And as I said in the lecture, we know the Big Bang happened, but we don't know, well, we don't know why it happened, but we don't know what went bang. And the reason for this is a perfectly reasonable question to ask. What was there before the Big Bang? Was dark energy before the Big Bang? It's a perfectly good question to ask, but unfortunately, science in the 21st century doesn't have an answer. But we know why we cannot answer the question, and that is because we know the laws of physics break down as we approach the Big Bang. So what happens in the universe today is that gravity, the force of gravity, which is described as relativity, is very separate from the quantum forces, quantum mechanics, the world of subatomic particles, the world that regulates the way atoms behave. Now, however, in the Big Bang, uniquely in the history of the universe, these two parts of physics, relativity and quantum physics, were relevant uniquely at the same time. And the problem is that whereas we have a beautiful theory of relativity and a wonderful theory of quantum physics, we don't have a theory that unifies those two. That theory would be called quantum gravity. Einstein actually, some people say, wasted the best years of his life trying to develop a theory of quantum gravity. And more recently, Stephen Hawking spent most of his life trying to come up with a theory of quantum gravity. And none of those two great minds succeeded. And so one day we hope somehow somebody will dream up or produce a theory that is valid and can be tested of quantum gravity. But so far we don't have that theory. And that's because of that, we cannot begin to answer the question of what was there before the Big Bang, or the specific question here as to whether the dark energy existed before the Big Bang. But it is a question that, of course, many physicists think about and discuss. I remember actually in Newcastle, I mentioned Alan Guth earlier on, who is the first person who discovered inflation. He was given a prize by Newcastle University many years ago. And I went to the dinner, and I was in charge of driving him back to his hotel. And I remember parking outside his hotel in Newcastle. I can't remember the name of the hotel, but it's a big, very nice hotel. And suddenly I look at my watch and I say, Alan, it's 4 a.m. We've been sitting in this car talking precisely about that. How did the universe begin? What was there? Could we conceive of something, some way to try and imagine where this vacuum energy comes from? Of course, we didn't conclude anything, but we had a very good time sitting in a car outside a hotel in Newcastle until 4 a.m. This is some years ago. I don't think I would do it again. So I'm wiser now. I know that question as of today has no answer.
Thank you. So here is the final question that we have time for. And it's, what would you say has been the most significant discovery during your lifetime?
Well, I mean, I've seen many wonderful things. For example, recently, many people might have heard about the discovery of gravitational waves, which are these waves of gravity emitted when black holes collide. That won another Nobel Prize 2 or 3 years ago. But I think I've seen the discovery of wonderful things like quasars and pulsars, the discovery of the Higgs boson. But I would say that in my mind, the biggest scientific discovery that I have ever witnessed was the discovery of that pattern of hot and cold spots in this heat left over from the Big Bang. That to me was really such an exciting moment because we knew it had to be there. We knew theory predicted, not just that they should be there, predicted the details of this complicated pattern. And so when that was discovered, I remember that quote I gave during the lecture, my "oh wow" quote. Well, that was on that Thursday, I remember, 22nd of April, and my telephone rang at 6 in the morning in Durham, and there was an American voice at the other end because the news had been embargoed, and because it was NASA very good at PR, so they embargoed the news at midnight. The embargo lifted. It was 6 a.m. in Durham. My phone rang. And there was this American voice asking me, what do you think about the discovery of these temperature irregularities in the heat left over from the Big Bang? I was stunned. All really I could say was, oh, wow. And that was really, I would say, possibly the highlight of, even though I had nothing to do with it. But I knew this discovery had to be made because I knew the theory and I've been working on the theory. And so it had to be there. So when it came, it was really absolutely amazing. I mean, every time I showed to my students that graph with the wiggles going up and down and the green line, the dots, I really have to stop because I've seen it hundreds of times in my life. And every time I see it, it's as exciting as it was the first day. So I would say that is the most important scientific discovery that I've seen. And that's considering so much that has happened in science over the last 30 or 40 years.
Thank you so much. That's all we have time for. So on your behalf, again, I would like to thank Professor Carlos Frenk. It would be much louder if we were in the lecture room. Thank you for just such an interesting and engaging talk. Thank you too to you, our audience, for watching. If you would like to give us any feedback, please do email us at public.lectures@ncl.ac.uk. Our next event is next Tuesday, the 27th of October, which I will chair again. It's by Professor Lee Cronin, and the title of his talk is The Robotic Alchemist: Digital Assembly of Drugs and Chemical Brains. So I hope you can join us the next time, and I hope you have a nice evening.